All right, let's look at wrapping up this warm-up problem from Monday, April 10th. So we were looking at the decomposition or splitting of water. And in our first two examples, we were looking at how we could change our mole quantities, what we had in our pantry, to from like whole numbers like 1 or 6 or 4 or whatever, and use our mole ratio, which is our recipe, to figure out what that would mean for how much of our products could actually be made. So this third part, C, is a little bit more difficult for a couple of reasons. Well, different. Because one, if you look at what's in our pantry, you'll notice that what's in our pantry is not something that is a whole number, right? I didn't say that we've got 10 moles or 0.25 moles even, which is something that's like an even quarter. I've got this kind of weird number, 5.41 moles, and I don't know how 5.41 moles relates to any of these coefficients given in my balanced chemical equation. And on top of that, I was told 5.41 moles of oxygen were made. So again, this is looking at kind of my pantry in the sense that I'm looking at what my dish looked like, meaning how much scrambled eggs I made or how many cookies I actually baked, and reverse engineering from that quantity of my dish what I had to have taken from my pantry. So this is kind of like our pantry, but reverse engineered. So we have two parts of this question. We want to know how many moles of water decomposed if 5.41 moles of oxygen were made, and then also how many moles of hydrogen gas made. So let's start with thinking about this again, our intuition. And as I kind of preface this problem, this is not one that comes easily to mind, right? Because I don't know how 5.41 relates to 2, 1, or 2, right? It's not an even multiple or percentage or fraction, right? So it looks like I am SOL when it comes to just trying to do this without showing any work, which, as you all know, I prefer anyway. So let's move on to the calculations. So how we're going to do this is we're always going to start with what we have in our pantry, or at least what we have in front of us that's a real lab quantity. So here in this example, that would be our 5.41 moles of oxygen. So we're looking at the dish that was made, and now we're going to reverse engineer, knowing what we know about the recipe, to figure out what that meant about how much stuff we used or stock we used from our pantry. So looking at my dimensional analysis, I want to cancel out moles of oxygen, and let's start first with our moles of water decomposed. So that means that I'm going to convert this mole quantity of oxygen into a mole quantity of water, and I can do that by looking at my recipe, which says that for every 1 mole of oxygen that was made, so that's that one coefficient out in front of my oxygen, that came from 2 moles of water being decomposed. So if I were to put in this mole ratio, I see that my mole oxygen per mole oxygen cancels. And if I were to then now take this 5.41 quantity and double it, which is what my dimensional analysis is telling me to do, I would get 10.82 moles of H2O decomposed. Now notice, I am being very particular and careful about how I am labeling everything. I'm not just labeling moles and moles and moles and moles, because when we do stoichiometry as chemists, we care about the mole quantity of one thing being different from the mole quantity of another thing, right? We care that a reactant is different from a product, or that there are two different products that could be made in a reaction, or that there are even multiple reactants that are involved to make multiple different products. So always, always, always include the label of what it is you're talking about when you're doing your stoichiometry. Okay, so we have taken care of moles of water decomposed. And now let's look at moles of H2 made. Now this is fun because we have two ways to do this now. So we could do this based on what we know about H2O and H2 mole ratio. And this is one where our intuition could probably come into play because if you notice, that ratio is 1:1, meaning for every 1 mole of hydrogen gas made, that came from 1 mole of water being decomposed. So I could probably predict using my intuition here and say that this will be equal to 10.82 moles H2 made. Or I could, again, demonstrate this quantitatively. So I could say that for 5.41 moles of oxygen generated, now I would need to look at the mole ratio that exists between oxygen and hydrogen. So instead of looking across the reaction arrow for mole ratios, I'm just looking at mole ratios of things that are made on the same product side. So I've got moles of oxygen that I want to cancel, leaving behind moles H2, which is what I want. And I know from my recipe, my balanced chemical equation, that for every 1 mole of oxygen made, there must have also been 2 moles of hydrogen gas made. So I need to double my 5.41 moles. This gives me 10.82 moles of H2 made. And what do you know? This matches our intuition. So in this class, if you're able to use your intuition, yes, absolutely do it. But do it as a means of proving to yourself that your calculations are right. Meaning, always show me your work, please. Show me the dimensional analysis. Show me these conversions using your mole ratios. I don't care if they have the same structure as mine. I just need to see your work and all your labels. And then you can kind of check after the fact that you're sane by using your intuition to figure out where you're going. You could also check beforehand to see like, oh, this is what I should get when I do my math. But always show your work when you're doing your stoichiometry. So we have completed the first task on our to-do list for the day, where we have looked at practicing stoichiometry. And that brings us to our next big topic in stoichiometry, which is the idea of a limiting reactant. So I will see you in part 2 of our lecture video series for Monday, April 10th, coming up next.